Let's look at divergence and curl, right? Before we look at these, let's define an operator called the del operator. So the del operator, del, D-E-L, the del operator is defined as it's like an inverted triangle. We call it del. D dx, d dy, d dz. So this is an operator because it operates on a vector field, and I'll show you how it operates on the vector field in an example. Now, if f is a vector field, say f is fgh. If f is a vector field in, say, R3, and the partial derivatives of f, g, and h exists, then we can define the following. We can define what the curl is, the curl of f. The curl of f is defined as a cross product, actually. It's curl of f, like this, is equal to del cross f. And how do we define this? We define it as I, j, k, d dx, d dy, d dz, and then you have f, g, h. So this is how you perform a cross product, if you remember when we did cross products. So we have del cross f is this quantity here. And what is this quantity? If we do the cross product, that would just be d dy times h. Think about it as a multiplication, but it's not a multiplication. You're just applying d dy to h. So d dy to h would just be dh dy, right? Minus d dz times g, which is just dg dz, all right, times I. So that would be the first component. By now, you know what the second component is going to be. It's going to be dh dx minus df dz, j. And then the third component is going to be plus dg dx minus df dy. Okay. So this is how you define the curl of f. F has to be a vector field to have a curl. Now, we can now define the divergence of f. The divergence of f is defined as follows. Div f, which is the del dot f, which is just d dx, d dy, d dz, dot f g h. So this is going to be df dx plus dg dy plus dh dz. So as you can see, the divergence is quite easy to compute. It's just applying the partial derivatives to f, g, and h and adding them up together. Find the partial derivative with respect to x of f, partial respect to g of y, partial respect to h of z, partial respect to partial respect to y of g, and then partial respect to z of h, and add them up together. So there is a glaring remark here that I don't want to miss. So something that we see that's clear is that the curl of f is a vector. Meanwhile, div f is a scalar. Curl of f is a vector, div f is a scalar. Now let's do some examples. So the first example is this. F of x, y, z, the vector field is x, y, I plus x, y, z, j, plus minus x squared, k. Okay. We're going to find the curl. Let's find the curl of f. So remember, curl of f is just del cross f, cross product, which is this matrix I, j, k, the determinant of the matrix, d dx, d dy, d dz. Then we have xy, xyz, and then we have negative x squared, okay? And then with this, we can do a lot now. So we take the partial, we have d, the first component will be, we'll just focus on this part because we're crossing off the rows of I and the columns of I. So what do we get? We get d negative x squared dy minus d of xyz dz. I, that's my I, plus d negative x squared dx minus d xy dz, j, and then we're going to add plus d xyz dx minus d xy dy. So if we perform all this operation, we're going to have 0 minus xy times I, right? dy, the partial with respect to y of negative x squared is just 0. The partial with respect to z of xyz is just xy. All right, I plus negative 2x minus 0 j plus yz minus xk. Okay, so we can simplify this a little bit further. This is negative xy I minus 2xj plus yz minus xk. Okay, so that's the curl. The curl is always a vector. Remember that. The divergence is always a scalar function. All right, so now let's look at a second problem, maybe a second part to the problem to find the divergence, which is always easier because scalars are easy to handle. Vectors can be a pain. I love vectors, but scalars are nicer. All right. So let's look at the divergence of f. So the divergence of f is del dot f, dot product. Dot product should always give you a scalar function. That means it doesn't have ijk, right? So the del is d dx, d dy, d dz, and then we're finding its dot product with xy, xyz, negative x squared, because f is that vector. So this is going to give us d dx of xy plus d dy of xyz plus d dz of negative x squared. What do we get? We just end up with y plus xz. Okay? Now, I'm going to give you some more remarks. In this video, I just want to show you how to calculate curl and divergence. That's the focus of this video. But there are some physical interpretations to this. A lot can be said about the physical interpretation, but I'm just going to say something very tiny, and we can talk more about it later on, in a velocity field. All right, so think about this. Let's say we have a river flowing, okay? We have a river flowing this way. Okay, so the velocity of whatever is flowing could be different at different points, okay, and so forth. Now, there is this what do I say? This forward linear velocity that is flowing in the direction of you say the forward direction maybe of the river, but there's also a circular motion. So wherever you are, let's say we have a particle around here, there is also a circular motion around that particle. Sometimes that circular motion is zero. There is no circular motion. But this circular motion rotates along an axis. It rotates along an axis. Okay. I think it's easier to do this. I'm going to do something. I hope I can do what I'm about to do. I want to get this and do it like this. Okay, very good. Ooh, I didn't know I could do that. All right, so this circular motion in this particle rotates along an axis that is normal to the flow of the river. Okay? This is the curl of the vector field, right? The vector field that is propelling the movement of the particle in this direction. Now, that's curl of F. Now, the divergence is the net change in velocity at each point. So we use the point here to do an example for curl. So if we pick a point, say we have a point here, all right? So the velocity before this point and after the point are different. So you have a longer vector before the point. So that means in this case, there will be a positive divergence. This is positive divergence. Now, if we have a particle around here, since the net change in velocity is zero, because this length, this vector is the same as that vector. The velocities before and after the particle are the same thing. This is zero divergence, all right? So in that case, a particle here, for instance, or let's use some other particle. The particle here, for instance, would be no. Let's use a particle over here. So this particle would have negative divergence. So that's a quick way of giving a physical interpretation to curl and divergence. And this is just in a velocity field. There are other ways of explaining curl and divergence in other types of vector field. Now, let's look at a few theorems that might arise from curl and divergence. a bunch of theorems. So the first theorem is this. Let's let phi be a function of x, y, and z. Okay? Phi, the gradient of phi is d phi dx, d phi dy, and d phi dz. Okay? Now, let's try to find the curl of this gradient, the curl of the gradient, because the gradient is a vector field, right? So, what do we have? We have I, j, k, d dx, d dy, d dz of d phi dx, d phi dy, d phi dz. Okay? So what do we have here? We're going to have d2 phi dy dz, right? Minus d2 phi dz dy. I, okay? All right. Minus d2 phi dx dz minus d2 phi dz dx. J d2 phi dx dy minus d2 phi dy dx. All right, do you see a pattern? So all I get here is 0i plus 0j plus 0k. And we're using the equality of mixed partials. So that means that d2 phi dx dz is the same thing with as d2 phi dz dx. And this is using Clairaut's theorem. That's Clairaut's theorem. All right. So we end up with 0. All right. So in general, the curl of the gradient of a function, a scalar function is a 0 vector, 0. Remember, curl is always a vector, so we expect our 0 to be a 0 vector. All right, so that's one theorem. Another way of explaining this is that we can conclude that this also implies that this also gives us a result that we're not expecting, and you'll see why. This also tells us that if F is a conservative field, then curl of F has to be 0, the 0 vector. Why? Because if we have a gradient vector, if F is conservative, then there is a gradient, there is a function such that F is the gradient vector of that function, right? Right? So if F is a gradient vector of that function, then curl of F has to be 0. Curl of F has to be 0. So those are the two two implications of what we have so far. Another one, the next theorem I want to point out, maybe this is 3. 2. Okay, I'm going to call it 2. Another one, I will let you figure this out. For any vector field F, the divergence of the curl of F is equal to 0. divergence of curl. We can find the divergence of the curl because curl is a vector, and we can always find the divergence of a vector. All right, let's look at let's try to develop another theorem. Let's assume that C is a closed curve in R2. All right, so we have our R2, that, and this. And then we have this closed curve, something like this. Okay? Think of a point here. This point, there is a tangent vector over here at the point, right? And there is a normal vector that is perpendicular to the tangent vector. So let's parameterize C as R of t is equal to x of t, y of t, okay? So with this, we can do a bunch of the regular things we know about tangent vectors. So that means the tangent vector is equal to r prime all over the magnitude of r prime, right? R prime is still a vector. All right, so in other words, this is the same thing as x prime of t over magnitude of r prime of t, right? And then y prime of t over magnitude of r prime of t. You see that? And if that's the case, n is tangent to t. N is perpendicular to t. So we can just find a vector that's perpendicular to t, a vector that when you do the the dot product, you get 0. So one candidate is y prime of t over magnitude of r prime of t, and then negative x prime of t magnitude of r prime of t. So my homework to you is to make sure that you need to check that this is n. If you want to check, t dot n has to give you 0. Okay? Because they're perpendicular. Okay. Now, we can do a bunch of things now. Let's assume we have a vector field. Now, let F be a vector field in R2, Fg, all right? Let it be a vector field. We can do the curl of F, even though it's not in R3. We're just going to assume that the third component is 0. So the curl of F is the determinant of I, j, k, and then we have d dx, d dy, and d dz. And then we have f, and then we have g, and we have 0. So this is just going to give us dg, dx minus df. Let's do one by one. The first component is I times d0 dy, right? d0 dy minus dz, but g is a function of x and y. So the first component is just going to have nothing, it's going to be 0. So what am I saying? I'm saying that the first component is d0 dy minus dg dz times I. But look at this, d0 dy is just 0. dg dz, g is a function of x and y. So maybe to make it a little bit clear, this is a function of x and y. G also is a function of x and y. So for that reason, this is just 0. This whole thing is 0. The same thing, if you also try to do the same thing for j, you also get 0, right? This is also going to give you 0. So the only one that works out is for k. So plus dg dx minus df dg of k. All right? Now remember what this is. Let's write it out. Curl of f now, if f is in R2, is dg dx minus df dy times k, right? So what do we have? And k, what is k? K is the vector 0, 0, 1. Okay. So what do we have now? We have this curl of f. I'm not going to write something. I'll remind you of something. Remember this underlined pink thing. Now, this means that I can rewrite my Green's theorem. So Green's theorem, which we know very well, can be stated in vector form as, remember this, f dot t ds, right, is equal to f dot dr is equal to curl of f times k dA. Curl of f is a vector and k is a vector. So let's put a dot here. Let's put a dot there and a dot here. Okay. Curl of f k. All right. Actually, we don't need the yeah, that's curl of f. We don't need the k here. We just, yeah, dA, curl of f dA. Okay, so this is another way of stating the Green's theorem. That, put it in green. Why not? All right, and this is called the curl form or the circulation form. Circulation form of Green's theorem. Okay, so we have something going on here. I'm going to call this part A of my derivation. Okay, now let's approach this from another perspective. Now let's consider the integral f dot n ds, which is the same thing as integral a to b, right, of f dot n r prime of t dt. Okay, so this is going to give you the integral a to b f dot g dot y prime of t minus x prime of t, right, times 1 over r prime of t times magnitude 1 over the magnitude of r prime of t over the magnitude of r prime of t dt. These two things will happily cancel out. And how did I get all these things? I went back to the fact that we have n. We defined our n up here. So I just took the n and stuck it in there, right? F dot n ds. That's what I wanted. Remember that f dot n is a scalar. So we're just doing a scalar integral, scalar line integral. What does this give us? this gives us this, that the integral from a to b of f y prime t dt minus g x prime of t dt is equal to the integral from a to b of f dy minus g dx, right? And this is now the integral. Going by Green's theorem, this is the integral over r. What is r? R is this region, right? Integral over r, double integral over r of df dx plus dg dy dA. Okay? And this is the same thing as the divergence, the integral over r of the divergence of f dA. So let's put this in a green box. Maybe not. Maybe let's write it out and put it in a green box. So what does this give us? This tells us that, where did we start? We started from here. Started from the bottom. Now we're here. Right? That's where we started. But where did we end? We ended up all the way here. My whole crew here. Put it there. So that's what we have. So whenever you have line integral, and this is over C, right? Line integral f dot n ds, where n is a normal vector, it's just divergence of f dA. And this is called the divergence form, or it is also called the flux form of Green's theorem. Of Green's theorem, there is no the in Green's theorem. Okay? So we have 3 theorems emerge from that. So the first one I really want you to remember is that the curl of the gradient of phi, if phi is a function of 3 variables, is 0. And this tells us that f is conservative if and only if curl of f is 0. Another one is the divergence of the curl is 0 also. All right? So the third one, go through it and really try to understand it, but I would expect a lot of questions. I would expect questions from this part, the third one. If you have any questions, email me or wait till we do it in class. But this should be easy. The example I gave you should be quite easy. Know how to do these examples. Know very well how to do it. And the 2 theorems. The theorem 1 and theorem 2. All right, I'll see you in class, or I'll see you in the next video if you're not